Hi, I'm Mark Kimmerly. I'm an integrated systems architect for Marvell. And I'd like to introduce a panel discussion on die-to-die interconnect. So we've assembled quite a range of experts from the field here. And our hope is to give an overview of each of our thoughts individually on this subject. And then we'd like to circle back as we wrap that up for detailed questions for the audience. As Bapi mentioned in the comments, you can find a pointer to Slido where we'd like you to go ahead and post your questions. If you see other questions out there that you'd like to, that you're very interested in the response, you can upvote them so that they get chosen first. With my introduction finished, I'd like to hand it over to Kenneth. Kenneth, can you introduce yourself as one of our distinguished panelists?
Thank you, Mark. Thank you, Bapi. Hi, good morning. First of all, wish you all and the families are safe and sound through this COVID-19 pandemic. My name is Kenneth Ma, and I'm a principal architect at Xilinx. My interest in ODSA is focused in driving the chiplet interface standard and also the ecosystems. And currently, I'm chairing the Open HPI work stream, and I'm glad to be here today with the PHY panel and to discuss with you and the other panelists. Thank you.
And Rishi?
Good afternoon. My name is Rishi Chugh. I am the VP of Product Marketing at Cadence, handling especially the IP division of Cadence. And my background has been on the PHY side. And it's a pleasure to be involved in the ODSA side of things and solving industry problems on the interconnectivity as we go to the next leap of our networking phase. And today you'll hear more about us on a collaborative effort of what we are planning to do on the Open HPI PHY side of things.
And Ramin?
Hi, my name is Ramin Farjad. I'm the CTO of networking at Marvell. And my interest with ODSA started with working with Mark and Bapi, trying to find a versatile die-to-die IP solution that can work over a wide range of internet substrates and packaging, which turned out to be both. And that's why I'm involved in this project.
And Manuel?
Yeah. Good morning, good afternoon. I am Manuel Mota. I am marketing manager at Synopsys, taking care of the high-speed interface IP portfolio, and in particular, with particular interest in this die-to-die IP portfolio, which includes both SerDes and HBI type of interfaces. And of course, my interest with in joining OCP and in particular this the ODSA efforts is to, of course, to enable market and help with this standardization efforts that we are commonly carrying on. Thank you.
Great, thanks, Manuel. And I'd like to go ahead and start off the discussion with just a very high-level overview of at least what I've seen in participating in the ODSA and what we've learned in trying to put together chiplet-based ecosystem. So maybe just to rewind back in time, we really kicked this project off with a multi-company effort to build this open chiplet ecosystem. So how can we put together systems out of chiplets? How can they talk together more efficiently? And through a lot of coaxing and cudgeling on Bapi's side, a lot of folks got together and built a fair amount of content into a white paper that really helped detail why building chiplet-based systems would be a good idea. And we certainly learned a lot in doing that, and it spawned a lot of other activities that kind of became what the ODSA subgroup of OCP is doing now. We learned through all of these efforts that chiplets could be a really good idea and could provide a similar benefit to technology scaling at a lower cost of integration. But what we learned through the effort is that they really, we need a good way for chiplets to be able to talk to each other so that we can be very efficient in that communication without burning too much extra power. So one of the other efforts that was put together as part of the ODSA was kind of a survey of different interfaces that were available in the industry. A lot of different options that we're currently looking at in terms of interfaces between chiplets and chiplet-based systems, with the far right side here really being the interface of the past, I'd say, kind of long-reach SerDes to go off chip. They could be used to go die to die, but don't make a lot of sense because of high power and complexity. A significant interest in the XSR SerDes in the industry, and lots of good efforts in standardization going on there. Excellent parameters on everything, but IP complexity is certainly far more challenging than a lot of other interfaces. I grouped together a whole bunch of different interfaces here under what I call a PIF, proprietary interface, kind of there are many different die-to-die interfaces being developed by many companies. And I think the key is there's lots of good options out there that have great specs, but the challenge is interoperability. So a couple of the efforts that the team on this panel are working on in the ODSA are what are shown here. There's an activity underway to define what we call a BOW, a bunch of wires interface, and also another activity to define open HBI. And certainly our panelists are, some of our panelists are experts on each of these fields. And what's very interesting is that, open HBI provides a low complexity chip-to-chip interconnectivity for chips that are already on a higher package complexity system. And a bunch of wires, I think Kenneth shared with me last night while we were reviewing our charts that I invented an analog OR gate here for the bunch of wires. And the goal really was to have a slider between bandwidth per chip edge and either package complexity or IP complexity. So part of the effort in defining that is to define something that could have multiple different modes, or could be put together on a finer bump pitch to yield high bandwidth where needed, or kept simple where it's not. Certainly interoperability is key on the bottom of this chart. And I think there's a lot of work going on right now in XSR SerDes, where we certainly see interoperability to interfaces of the past and the future. And our goals, I think, as bringing BOW and Open HBI through OCP, are to go from relatively low interoperability or kind of medium interoperability based on HBM specs, and push things into the open, so that different companies can build interfaces that get us to much more interoperability for these interfaces. So I just filtered out the stuff that was high power, or really without easy options for interoperability to leave us with. The three interfaces that I think are our main focus for today's discussion, and just to kind of highlight to people where our thinking is at this time. So I guess my summary, and before we move into a brief discussion from each of the panelists, I certainly see that there's a number of different applications and a need for different interfaces, where standards-based and SerDes-based interoperability could be really, really powerful, because there's a fair amount of chiplets that are on the market or coming to the market that would have a serial interface, and we could be interoperable with them. And I think that the two open interfaces that we'll be talking about today and that are underway within ODSA kind of fit different application space, where a chip integrator might not necessarily need that kind of IP complexity to build an interface between multiple chiplets. And I just want to leave everybody with the thought. We're very interested in your feedback and your participation in this discussion to learn what the community really needs in an interface moving forward. So with that, I'm going to save my call to action for the end of the presentation and stop sharing, and we'll switch over to Kenneth Ma from Xilinx to take us through his thoughts. Kenneth, it's all yours.
Thank you. So thanks again, Mark. Hi all. The original panel title, I don't know whether you guys have seen in the recent invite. The concept is whether a single open PHY can rule it all. So my short presentation is centered around that theme, but then of course, Mark already gave the introduction that there will be several options out there. But Mark already gave a great introduction, and I'm trying to build on that and then add a few additional comments while giving a brief intro to the OpenHPI. I understand that Rishi will talk more about his idea on the OpenHPI as well. So question is there an ideal universal open PHY for chiplet? What does it exist, and what does it take to actually rule it all? So in order to do that, you need to have an excellent PPA, power performance area, extremely scalable, near zero latency, and the BER, very flexible reach, flexible bump pitch, support flexible media, interposer, organic, very broad process node support, and support the 2.5D, 3D, or 2.xD implementations, interoperable with its own future generation, forward, backward, and the other IOs, 5 similar technologies. And the key is also mappable to many protocol and transport layers conveniently and seamlessly, very low cost, easy to manufacture, and easy to test. And of course, we know this thing doesn't exist, right? So life is full of trade-off, and usually it is the use case that will dictate some of your design target. And we also know that the bandwidth, latency, and the reach will kind of interrelated with the link rates and the BER. Nominally, the relationship that I show is roughly interrelated. They're not linear for sure, but then this is roughly how they would correlate in the real life. The trace length, longer trace length will usually increase your picture per bit. Your bit error rate also increases, and then in order to fix that, then your latency also increases, etc. Another big category of trade-off is whether you choose the wide parallel versus the serial, and then subsequent to that is whether you choose the interposer and also the organic substrate as part of their choices. On the right, there's a chart from IBM presentation in the September workshop. They actually show different characteristics of the board level SerDes versus the module optimized SerDes, and also the wide on module bus, or the chiplet bus in this case. And you can see they have different characteristics, and the wide is parallel, excel on the latency and the energy front. But then the other practical challenges like the design complexity, IP availability, interoperability. I mean, usually you have your set of IP providers and design choices and tools that you use, and also the supply chain, whoever is a packaging house or fab houses and other things. You cannot change very easily just because you want to have certain use cases, and then some of them will dictate your choices as well. So those kind of a trade-off is not easy to overcome sometimes, and the business model as well, right? So from our view is very simply that the wide parallel and the SerDes will continue to coexist, and no one size fits all, and then they will complement each other. I have some cartoon on the bottom right that actually shows some of them. Some of them actually have a serial and parallel in the together, but then not all of them are simultaneously chiplet interface. But then you can use parallel to connect to the chiplet that is doing SerDes or doing the optics. But then the chiplet interface in this example, they're actually the wide parallel in order to carry very low energy bits to the chiplet, to the external world. But then if you look at the left side of the boxes, the use cases, you have the, if it is short reach, very power and latency sensitive, we think that the wide parallel suits better. If it is a long reach and the board-to-board, so this should better, which Mark also mentioned. If it is a 2.5D, then it's use case dependent. And then, both of them seems to suit in different use cases. The 3D die-to-die in the future, however, the wide parallels, we believe it should much better, because ultimately, in order to make all the dies to work seamlessly together like a single monolithic die, you need the extremely low latency and then the low bandwidth. No power options in order to make them work. and you don't want to have the hotspot, so the energy per bit is also important there. So, but one thing that will make it success is the time to market and the low resistance to adoption. So, as far as we can leverage the existing technology and make it low resistant to adopt, that's what we are trying to do with the OpenHPI. Within the SerDes and the parallel world, there's also one additional choice is that the wide parallel can also be fine pitch and coarse pitch. So if you look at the table, which is like a subset of what Mark has shown, but then pay attention to the bump per lane density columns is that they are almost like a 1 or 2 order of magnitude differences in terms of the density at the pitch front. The SerDes is much higher bandwidth, the per lane. But then because of the bump lane density is lower, so that ultimately at the if you need your bandwidth density to be highest possible, the fine pitch state of the art is still almost an order of magnitude higher than the other options. And of course, the trade-off again is area bandwidth density requirements, your energy per bit requirement, but ultimately the design cost and manufacturing cost, which the fine pitch, especially using the silicon interposer today, is more expensive. That's for sure. So one food for thought is whether we can actually have a fine pitch to interrupt with the coarse pitch design through some kind of the either RDL or other way to allow a fine pitch design to go coarse pitch for the use cases that don't need that much bandwidth. But then that is just a food for thought. One slight introduction to OpenHPI. We basically is trying to leverage proven JEDEC HBM standard. As you may know, the HBM3 standard is coming. We are trying to leverage the existing and the proven the PHY technology, the state-of-the-art electricals, and we can further optimize them because the HBM, the channel is longer because the way the HBM memory is constructed, but then the chiplet is a die-edge to die-edge. They are much shorter channel, and we can further optimize them. And then we can leverage the PHY, the IP experience, and the test ecosystems. And again, the manufacturability, including the lane repair capabilities, are something that we can directly leverage from. The tables show, I won't go through the details, but it's a suffix to say that most of the key metrics from the energy per bit, the bandwidth per pin or per millimeter, those key metrics are pretty much a state-of-the-art for the fine pitch OpenHPI. But then the cost is something that either we have to, bite the bullet or overcome. But with the next generation, the wafer level, the integrated fan-out technology coming, and especially they are also improving the media, the channel characteristic, as well as the performance. So we believe that the cost will come down, and together with the enhancement when those new technology comes. So the last slide is just call to action. If you're interested, please join ODSA and the technical work streams. And then if you're interested in the OpenHPI work stream, please do email me or Papi, and the email is here in the screen. And with that, thank you very much, and I pass it back to Mark.
Great, thank you so much, Kenneth. And in the interest of time, and by the way, thank you very much for keeping to our schedule for today. Let's pass the baton over to Rishi to go through your introductory presentation.
So if you look at the die-to-die interconnect trade-offs, right, this particular technology has been there in the industry for almost 5 years now. We see key OEM partners having merchant silicon which have used die-to-die interconnects, and this is all in public information. And what's happened over the period of time is everybody comes to an IP house and they basically provide their sets of requirements. And overall for the industry, as well as from a business point of view, it's not a scalable model. We all acknowledge that. Plus, as the designs are getting much more complex and the turnaround times have shrunk significantly, people want to leverage as much as possible on their investments. And more so ever, it also reduces the BOM cost when folks try to mix and match different dies and get something out of it. And it is very much prevalent because you see most of these OEMs having different solutions in silicon. They might have an independent NIC card, they might have a CPU, they might have an offload engine or an accelerator for AI ML. And it makes more sense to get an optimized solution in silicon when all of them have been integrated together. And each of these applications have their own quirks or own requirements as such. And there are various factors, as Ken had mentioned. There can be packaging challenges, there are beachfront and bandwidth issues, if it's a networking or a CPU type of a SoC, or if it's a standard SoC which goes as a machine learning or an AI. And even from a PHY point of view, when we look at the PHY point of view, where we are going to focus more today, it's basically what standards are you going to use? Are you going to use a proprietary? Are you going to use the conventional NRZ or a PAM4? And the power requirements, which is directly tied up to your packaging challenges, the thermal budget associated with that SoC. And most, but not the, but the most, another most critical aspect is even the latency part of it. If it's a CPU architecture or if it's an AI ML type of an application, latency plays a very important role. And we have seen that the main crust of this particular session and or the ODSA is so that we have a unified ecosystem going forward where we can leverage each other's skill sets, investments, and try to solve a problem in the industry, which is very much prevalent. And clearly, one type of a solution doesn't fit for all type of a die-to-die connectivity. We do acknowledge that fact. And that's why we are trying to basically address in different segments. Already the optical guys in terms of MSA standards and the CEI, they have basically identified as a 112 gig XSR, which was even there in the 56 gig side of things. They have a benchmark or they have a spec where they want to do the optical engine connectivity within the die, and that's been established. But on the data path or on the custom side, there's still a lot of ambiguity over it. So what options are we looking at over here? So there's basically a parallel interface. Then there is a normal NRZ interface, which I would say proprietary. People are basically using it, and Cadence is a victim of that. I should admit that. We do have something called as the Ultra Link 5, which we announced last year, and it's been available in both the foundries, and definitely there are active customer engagements over it. But as I said, I do admit that that model is not specifically scalable and not widely deployed in the industry. And then comes the PAM4, where again, we have the CIE OIF specs, and it's much more standardized. It's being used for optical engine or for photonics integration into the monolithic die. But it has its quirks as it comes because it's a full-fledged CDR system, and you cannot scale it to have terabits of data being transferred using such type of an interfaces. It will just not be practical to have a monolithic die with terabits of data being transferred and using a PAM4 type of a signaling methodology in it. And we can have this discussion offline. We do have a IP on it. And most ever, people also need to be educated about how the things are. There needs to be a standard, because otherwise what happens is every specific vendor or a provider comes up with his own PPA and a data sheet, and it can be misleading, or I would say it won't give you the details as you would be requiring when you start integrating it. Is it a true CDR? Is it clock forwarding? And there's a difference in nomenclature, and people have a lot of ambiguity exactly as to what they are getting. And later on in the design methodology, when they start integrating, they said, oh my God, I didn't know about this, or I didn't know the consequences of this. So we have to look collectively with all the experts over here and industry panel, where we can basically come up with something which has a clear direction, a clear usage model, and more so ever the interoperability, where we can reuse our skill sets, our solutions to solve this problem in the industry. So focusing back on the HBI 5 by itself, so this is a proposal. It's subject to change, and the dialogue is all going on right now. So the solution can be basically leveraging on our proven HBM and DDR technology. There's already a JEDEC spec for it, and it's basically using and exploiting the PHY technology from there and leveraging it for chiplet technology. So we can basically look at the DDR training schemes. We can look at the IO technology, which is supporting the HBM2 and HBM3 signaling, and it's pretty much defined, and HBM3 is ongoing, I would say. And it has all the essentials of a PHY, which would meet the requirements of a chiplet integration in terms of per bit lane deskewing. You have a master N on one side, and also the deskew is basically well defined, and it gives you a very low overall system latency. And of course, there are some caveats, as Kenneth also mentioned, that about the reach and what can we define on chiplets, what application can we go into it, and every application will deviate or make the PHY deviate from the usage model. And that's what we want to basically identify, which is the best usage model for what class of applications over here. And again, the scene has not changed much. What we're looking at over here is one of the specs what we can look at. And of course, this spec is subject to change as the standards evolve, is looking at an area parameter, looking at a round trip latency, looking at the power efficiency. I think so most of these are in the ballpark what industry wants and what folks are basically discussing over here. The data rate over here, we have said up to 4 gigabits per second. But again, as you look at the HBM3 standards, it can scale to beyond 6 gig also. So that doesn't prevent it from happening. And also the total bandwidth, what we see at the PHY, that is TX and RX, looking at a 124-bit wide of PHY, the total bandwidth density associated with it, and what beachfront are we looking at? Because that basically defines how much of data we can send through it. Right now, our focus is on the PHY side of the things. Of course, there is another whole league of the link layer associated with it, and that's a separate discussion, but that's also ongoing from an industry standard and specs point of view. And the key essential part is we want to make it something like PCI Gen 5 type of a thing, like a pipe 5, where the controller and the PHY are much more unified, the interface is unified, and there can be a mix match, there can be a marriage of two different organizations, one the PHY and one the link layer, or the vendor can decide or design his own link layer for whatever reasons what he wants to do, depending upon his data path, and still use the standard PHY so that he can do interoperability with adjacent die sitting on the other side. Going a deep dive into the stuff of the things, and again, these slides will be shared. I don't want to go to the whole details, but overall, we're looking at a very comprehensive features of the PHY, not only from the elements of PPA, which is basically the power, the latency, and the area, but also what are the system testability features associated with it. What do we want to put inside this PHY so that when we do wafer level testing or silicon level testing on this, we get the right sense in terms of our yield targets. And that's very essential for such type of designs because it's very intrigued, and we have to factor into all these standards which go into the PHY. And that's what we want to bring it up on the table, that what we want to do over here is define the clocking methodology, define the data path technologies, what are associated with it, the electrical characteristics of the PHY by itself, and then also the testability aspect of the PHY. And again, there are differences in the core supply voltages based on whether we take the HBM3 technology into floor or whether we take the HBM2 technology. Again, those are all open-ended stuff, and we can have variants of both depending upon the design and the process mode, because there will be an element of the process technology dependency also on this implementation. Again, going into further details of flow planning, and I won't spend more time into it, but I will share these slides, and if there are follow-up questions, that how does the HBM array calculation happens, and how much are we looking at the number of pins per slice per PHY, and how the flow plan looks associated with this in terms of the show line, in terms of the bandwidth and the data path. And when we connect it to an interposer, we are looking at what length and estimated channels, what we are looking for the interposer side of things. So again, this is dependent upon the package technology. Right now, we are looking at the reach of like 3 to 4 millimeters. But then again, if you look at the HBM spec by such, because it has a different constraints applied to it from the controller and the PHY module by itself, the PHY die, they can go up to like 10 millimeters or larger than 3 or 4 what we are specing. Again, these are all the stuff what the forum over here we are discussing. We are having our weekly meetings, and this is something where Cadence is committed to provide a solution, working with the partners and contributing at the specs side of things. So with that, I had this in my presentation, and if there are any follow-up questions, I'll be more than happy to take it in the forum.
Good morning, everyone. In this talk, I'm going to cover the BOW interface and the packaging options that BOW can address for die-to-die connectivity. So first, starting with the BOW objectives and how we started to put together such an interface, and what was the original goal, was to come up with a versatile die-to-die interface that can work across wide range of packaging solution, all the way from silicon interposer to organic substrate. And that was mainly because of the need of the industry, that some people were already, on the memory side, had interfaces that preferred the type of high bandwidth but low speed type of IOs because of the limitations of the technology on, let's say, memory chips. And also on the other end were solutions that they wanted like low cost. They couldn't afford the high cost of the interposer. So that's why we put together this set of objectives for BOW. I'm sure if you have been involved with ODSA, you're familiar with these requirements. I quickly go over them. That of course the throughput or the bandwidth per chip edge is one of the key requirements for these interfaces, and we wanted to divide it into two sections. One is like a simple I/O interface that can be implemented anywhere, like a basic CMOS I/O, and also simple packaging like organic. The bandwidth for that we limited it to about like 0.1 terabit per millimeter. And that's for the solutions that you don't necessarily need a very high bandwidth, very advanced. At the same time, you can benefit from very low cost, both on packaging side and the interface design. But on the other side, you can go advanced on the packaging, either high cost packaging or high cost or high complexity IP to get to a terabit per second and so forth. Of course, the other metrics like power, BER, latency, and reach are important pieces of it that you're familiar with the requirements. I'm not going to cover it. And of course, because a single I/O interface does not necessarily mean that you can run it at super high speed or like high density and so forth. One of our requirements was that to make this every generation that gets faster in speed and higher performance at least be backward compatible with the generation before. The other requirements, of course, were like a minimum cost and complexity, and also the time to market. These are super important. You don't want to have a chip one of the main reasons that people are going to our chiplet architecture is to lower the cost and also lower the time to market, such that, let's say, complex analog IPs or RF IPs that will take a long time will not slow down the basically introduction of the new DSP chip or the digital chip to the market because of that. That usually digital processors or digital chips can be implemented much faster. So that was one of the requirements of that. Also, the reason that we went on the parallel side, because in certain cases that you need FEC, if we just go serial for an FEC scenario, we have to up the speed to fit in the overhead of a FEC and then down the speed. And in those cases, you need like 2 PLs and so forth. But going with the parallel option, you can keep the speed the same, just add an extra bump. And at the same time, of course, while we meet these requirements, satisfy all the performance, power, latency on organic substrate with the advanced version of it, while it's easy to develop into different process nodes all the way down to 28 nanometer. At the same time, because we wanted to be versatile, we wanted to be in a solution that can also work over silicon interposers or info package integrated fan-out. Testing is an important piece of it because in volume production, we need to have a good test, otherwise the yield will kill the whole cost advantage, and preferably not be in have any licensing costs to make it easy for people to use. So Bo breaks down into two modes. Generally, the simple version of the basic CMOS I/O that is unterminated, and depending on what lens you want to run it, you can basically use a higher speed to go lower length, or lower speed like up to 4 gig to go to 5 millimeter. But once you terminate it, you can go to much higher speed and longer range. The first generation of both terminated goes to 16 gig per wire, up to 50 millimeter. So this is the bump map for the bow, and of course for the bump map is a common bump map that you can use both for unterminated and terminated. So they can be easily backward compatible. The error correction bits or bump is simply added. One can use it or not, but it doesn't affect the speed or the baud rate of the whole channel. And you can stack them up to get higher and higher bandwidth. For example, you can stack up to four of them in a scenario that we've implemented, and we can go to get to a terabit per second here. So different applications, of course, over silicon interposer, you can easily use the unterminated, the simplified version, same for the EMIB solution. But to go, you can also go to bow terminated, or use a bow that is already with termination option, and activate it to go to higher speeds over the limited density of the traces of an organic package, and it still get the same or similar bandwidth advantage, close. But at the same time, you can, if you do not need a high bandwidth between two chips, you don't have to use the silicon interposer, and you don't have to have a design that goes up to 16 gig with termination. You can still use the simple bow unterminated and connected the two chips together on a silicon, organic package, and benefit from the advantages. So that's one of the key advantages that bow offers, that it gives you the flexibility that depending on the need that you have, you can go high speed, high cost, or high speed, more complexity on the interface. Or if you don't need to go that, you can use low complexity and also low cost package. Of course, the integrated fan-out, the wafer level packaging is something that is coming to the industry more and more, and people started to using it. It has the advantage that from the cost point of view, is very similar to the MCM and organic package, so that's a big advantage of it. But it also provides 3x the density of the wires from the RDL layers between the two chips. So bow actually, in an unterminated way, can play a big role here and provide good higher density at a similar cost per se, maybe 3x the density. One of the advantages, of course, bow will have, if you have your die implemented integrated with bow, is that it can give you low-cost 3D packaging. When you have basically these info chips that are integrated, this is the way, if we call this one info chip, that are integrated together, you can stack them on top of each other and connect them with through mold vias. These through mold vias are similar to through silicon vias, TSVs, but their density is much less. But to get the same bandwidth, of course, you need to push more bandwidth per via. And that's an advantage at bow terminated with the 16 gig per line will give you, and it enables you to create a 3D high bandwidth connectivity at low cost. The cost of these through mold vias are fairly low, as much less than a TSV, and it gets you the same type of bandwidth. So this is another advantage of a chip integrated with bow that has the option to go with termination. So here is a comparison table between the solutions that are targeted for interposer and also the solutions on the right that are targeted for organic substrate. Of course, bow is the one that covers both of these categories, both interposer and the unterminated version, and the organic in both unterminated and terminated, as I shared. From performance metric, it's bow, like over the interposer, bow and HPI and NBIO. They are very similar in terms of bandwidth and power and so forth. Their advantages and features are very similar, of course. But of course, bow gives you the advantage that it can operate also over the interposer, sorry, the organic versions that are low cost. And of course, the bandwidth of the bow unterminated drops when you go to organic. But if you have a terminated version of that, you can go closer to a terabit per second. And of course, the other two scenarios, like the two interface IPs, are AQ-Link and XSR, that most people are familiar with XSR. And AQ-Link is a design that we have done that is, let's say, backward compatible to bow, but it gives you twice the bandwidth of bow terminated. So you can go to very high speed in terms of bandwidth on an organic substrate, and with fairly low power advantage. It gives you similar power advantage as the solutions over silicon interposer. So this is a simplified table for 3 or 4 main types of interconnects. The first one is the interfaces over a silicon interposer. The second one is bow over organic. Then we have XSR, of course, and AQ-Link, which is a proprietary solution. From power efficiency, of course, as you saw, these guys basically HBI, bow, on both unterminated or terminated are about 0.6 to 0.7 type picojoule per bit. XSR is about 1.5, so it's higher than all these, and the AQ-Link is still in the 5.6 range. From shoreline bandwidth density, basically both terminated would fall a little bit short below 1 terabit per second because it's organic, but all the other ones will give you over 1.5 terabits per second. And what I should add, by bandwidth, the terminology I use is transmit plus receive bandwidth, not just like half of it. Some, I guess, the Rishi in previous simulation presentation I used. On the latency side, of course, XSR will fall short because it has used the FEC to get to the target BER. Design side, the cost of the design and complexity, the solutions over silicon interposer, of course, are the simplest. It's as simple as a CMOS IO, so that they are the winner. The bow termination and AQ-Link, they're NRZ solutions, so they're not as easy, but easier than a PAM4. That's why I listed it like this. But of course, from product cost, interposer is a high cost, but the all other ones run on organic and low cost options. And the last one shows like which one are standard or not. That helps with in the ecosystem you wanted to use. So in summary, basically bow as a simple unterminated solution facilitates the use in a wide range of ASIC user applications that use the interposer, and very fast to develop and integrate. The higher speed version of it, which is the terminated one, will enable high bandwidth connectivity on low cost organic packages, and the next generations we're targeting even higher than 1 terabit per millimeter. And the good things about it is that it's backward compatible. Once you put latest generation of both, it can backward compatible work with other chiplets in the market that run at lower speed. And basically, at the end of the day, bow with the current solutions and features that we've defined, it enables a wide range of applications, from interposer to organic, and also info. And we try to get more feedback and more contributions from the industry to be able to come up with the final solution that will satisfy the needs of most people across a wide range. So that concludes my talk.
We'll quickly switch over to Manuel to share your thoughts about the interfaces.
Okay, very good. So this was the question that we were originally posed to ask to answer. Is will there be a one PHY for one die-to-die PHY to rule them all? And you know, I've tried to look at this from a high level perspective to try to understand what were the issues that we were trying to address, and if they could be addressed with a single PHY. I think you know the conclusion, but I will go through my thought process and share it with you. So let's start. So in order to answer this question that we were asked to answer, it's worth looking at the nature of the chiplet die-to-die market. And I think the keywords that best describe this market are really diversity and alternatives. We've seen that in previous presentation. There is a multitude of alternatives and a diversity of requirements. First, okay, so we have to start with, we have two very diverse fundamental use cases with different care-abouts that drive their decisions with respect to the PHY and other aspects of the design. The die disaggregation drive is motivated by the need to split the big SoC for manufacturing or economic efficiency, as well as improved product scalability. Think about multiple SKUs based on the same dies, etc. In these cases, the same die is present in both sides of the die-to-die connection, so that there is no immediate need of standardization. However, of course, there is a potential and a very real future-proof and cost advantages in pursuing standardization and relying on standardization. Designs following this path are care about throughput, care about power efficiency, care about latency. And alternatively, the package integration drive is motivated by bringing to the same package different functions for improved time to market, for cost, for flexibility. These dies are optimally implemented in different processes. So again, think about an RF or an IO die that is implemented in some older node, and that then is packaged together with a digital processor that die that it's in a very advanced or cutting edge node. In this case, the die on both ends may originate from different vendors, so it does not have to come from the same, the same design house, the same vendor, and thus standard adoption is critical to enable the chiplet marketplace to take, to take advantage of this drive. Designs following this direction, then care about cost, care about standardization, etc. And that, looking at it from another direction, also from packaging technology perspective, there are alternatives, they actually abound. They range from organic substrate-based packaging, which is typically low cost and simple, but on the other hand, it has low, it is able to do only low routing density, and all the way to silicon interposers and bridges, and bridges like shown on the right side of the slide, and these feature the highest routing density, but on the other hand, they are much more complex and higher cost. Recently, of course, there is also a lot of interest in the market about info integrated funnel technologies with very interesting proposals that fill or try to bridge the gap between the organic substrates and the interposers by allowing higher routing density than organic substrates, but at the same time a much lower price point than silicon interposer. So again, alternatives, again, a diversity. This diversity is also, this diversity of use cases and packaging options, they do influence the PHY options, and that system designers have to take. But this landscape can ultimately be segmented into two main alternatives from the PHY architecture perspective. On one side we have the high-speed ZS-based PHY architectures. On the other side, there is of course the low-speed wide parallel-based PHY architectures, and there are, as we've seen before, various declinations of each type of architecture. In a simplistic but I think realistic way, we can say that for systems that must use interposer-based packages, for example, if they use HBM, that requires high density routing on the package, HBM memories, I mean, the low-speed parallel-based PHY architectures are best suited because they take advantage of the high-density routing available in the interposer, while not being impacted by the high-speed limitations or the speed limitations of channels routed on interposers. Conversely, for systems that do not need the silicon interposer-based packages, then they can take advantage of the good high-speed characteristics of the channel on an organic substrate, and therefore can rely on high-speed ZS-based PHY architectures, that do not require high-density routing to deliver the high throughput that is required in a lot of these use cases. In summary, the type of memory and the package technology used in the system, it plays a significant role in determining the type of PHY architecture that will be selected, and so in determining the need of the availability of multiple PHY architectures in the market, coexisting in the market to serve all the requirements. This slide is really just a simplistic way to capture the key care-abouts of any die-to-die connection. This has been approached before. I think it's kind of the same idea. There are basically, or fundamentally, there are 5 or 6 key care-abouts when you're looking at a PHY and at the die-to-die interconnect. These are bandwidth efficiency, power efficiency, latency, reach, as well as bit error rate, and of course cost. And this, I will not go in details in this slide. I think we've discussed this. Other panelists have already shown similar information. But there are more care-abouts when you're selecting the PHY, and then they should be addressed by the technology you're selecting. So for instance, packaging and assembly costs. For example, a CERDES PHY does not require high density packaging, whereas a parallel PHY often aligns with HBM requirements for packaging, so requiring being implemented on high density or silicon interposer type of packaging. Process technology, again, how easy is it to port the PHY architecture to multiple processes and to multiple nodes? Are these ports available in the market already? Some systems will have very specific requirements that may make porting more challenging. I am thinking, for instance, of RF, analog, or sensor optimized processes where technology may not be amenable to some architectures, or at least not optimized for those. Finally, design for testability and ability to determine known good dies before assembling in package, enabling self-contained testing at wafer level or during production, and adhering to testability standard interfaces and methodologies are also important criteria for die-to-die interface selection. Again, keeping in mind that once the dies are assembled into the package, the die-to-die PHY is no longer accessible from the pins of the package. But even if we looking from the PHY towards the inside of the SoC, this is the interface towards the SoC is another area where standardization is required and helps to accelerate adoption. But again, there is diversity. Again, there may be a need to for different options to coexist. If you look at the two main use cases that we defined originally, their different goals also may lead to quite different options. In the case of die disaggregation, I think in that case, die-to-die optimized protocols with very low latency and very low complexity are preferred. Initially, or in the initial stages of the market maturity, these protocols are typically proprietary, but I do expect that they will evolve towards standards-based solutions. As standards evolve, and OCP is obviously a big player in this effort. In case of package of the package integration, direction, then the main objective is to accelerate time to market and simplify adoption. For this, in this case, it may make more sense, or a better sense, to adapt and reuse existing chip-to-chip protocols and controllers that are readily available and can be easily adopted. So again, choices, again, alternatives. So regardless, in summary, regardless of the direction or of the perspective from which the die-to-die market is approached or observed, there is no single PHY architecture that meets the needs of all use cases. There are fundamentally different package technology characteristics that are not bridgeable with a single PHY for important use cases, and other trade-offs, other trade-off requirement, or the trade-off of other requirements in different use cases may also drive, divergent PHY needs. In any case, obviously the standardization efforts are desired and required to support solutions for all use cases. But we do need more. But we do need more than a single PHY architecture. So we need solutions based on high-speed CERDES PHY, like the USR XSR PHY that we has been touched upon before, but also based on parallel PHYs, which was covered on in more detail in most of these previous presentations. And they both architectures must coexist in the chiplet market space, in my opinion. And this is the reason, obviously, because this is Synopsys' opinion. It's also the reason why Synopsys IP portfolio includes state-of-the-art, high-speed 112 gig CERDES die-to-die CERDES PHYs optimized for ultra-short reach, extra short reach, so for die-to-die connectivity, as well as wide parallel HBI PHY IP. With that we can support our all the different use cases that we've seen here, all the different options that I've touched upon in this presentation, and that are based on what we observe when working with our customers to serve them. And with that, I conclude my presentation. Thank you.
Great. Thanks so much, Manuel. That was a very insightful presentation. I just want to wrap up our discussion today. Thank our excellent panelists. Thank you, Kenneth. Thank you, Rishi, and Ramin, and Manuel for your very informative talks today. I want to finish up our discussion with just a call to action. There's a lot of good work being put in by a lot of hardworking people within ODSA to help define this next generation chiplet-based communication. We've got regular work groups set up both for bunch of wires and OpenHBI, and lots of other work groups, Kenneth, as you mentioned, on building that stack up beyond those interface PHYs themselves. So please come join our team and get together with us and help us put together the chiplet-based systems of the future. Our link is right here. You can access all the information that we've discussed in the past, and we'll work to put the information from the discussion today onto our wiki as well. As always, thank you, Bapi, our Master of Ceremonies, for roping us all into this great discussion. And thanks to everybody who joined in today.
So hi, this is Rishi here. I believe there are a few Q&A questions. I'll take one of them, which is on the BOW and the OpenHBI as competing standards. I wouldn't classify them as competing standards. Every specific application and deployment of chiplet has a specific use case. There are trade-offs with three different, I would say, chiplet standards. What we have, one is the XSR, BOW, or even the HBI. Based on your application requirements and the PPA requirements for it, your design requirements, both of these standards will be running in parallel. Definitely, there will be a commonality in terms of the link layer aspect of these two. The PHY aspect will be changing based on your requirements.